Welcome you all. We will discuss today about a steady flow energy equation. Basically, this equation is applied for open system because as you know that in open system both mass interaction and energy interaction can be taken place across the boundary of system. So basically this equation deals with open system. As in this figure, it is clear that this is open system. How? Because in the system some quantity of air, this is m kg of air, enters inside the system and same quantity of air exit from the system, right? The n kg of air enters inside the system and same quantity of air exit from the system. That means this exchange of mass interaction is taking place. Okay. Next, this Q amount of heat is supplied to the system and this work output is done from the system. That means in this condition both energy, that means whenever heat is supplied, this we get some work output. That means in this system both mass interaction and energy interaction are taking place. That's why this is called open system. Okay, so first of all we need to understand what is this open system, and for open system this steady flow energy equation is used. Okay, so both mass and heat interaction are taking place across the boundary of the system, right? Okay, let me start regarding this one. So as we have discussed earlier, this is the open system, right? In this open system, this is the entry point and this is exit point. From entry, the m kg of air enters inside the system. Well, so at inlet, this m kg of air enters inside the system. At inlet, these are the properties of the air at inlet. Okay, so this is explained here. This U1 is a specific internal energy. That means U1 is the specific internal energy of air at inlet. P1, this is the pressure of air at inlet. B1, small b1, this is small b1, this is a specific volume at inlet. This is b1, this is velocity of air at inlet. This is h1, this h1 is the specific enthalpy of air at inlet. So these are the properties of air at the inlet of the system. So okay, so U1 is the specific internal energy, P1 is the pressure, small b1 is a specific volume, b1 is the velocity of air, and h1 is the specific enthalpy of air at inlet of system, right? One more term we will use, this is m dot, right? So this m dot is the mass flow rate of air. So there is difference between m and m dot. M is the only mass of air, that means its unit will be in kilogram, but this m dot, this is the mass flow rate of air inside the system. This unit will be kg per second. So we will use this term later on. So just there should not be any confusion between this m and m dot, right? Okay. So these are the properties of air at an inlet of the system. Similarly, this is outlet. The same quantity of air, that is m kg of air, enters inside the system, and the same quantity, that is m kg of air, exit from the system. This is the output of the system. At an exit, these are the properties. This is the U2, a specific internal energy. P2 is the pressure. A small b2 is the specific volume. V2 dash, this is velocity. This H2 is the specific enthalpy. These all are properties of air at an exit of that is an output of the system. Okay, this is the exit outlet of the system. Okay, right? Well, so this is and one more term is there. This m. This is our datum line. Okay, this is my datum line. This from this datum line, this Z1 is the height of this entry. Okay, so what is this Z1? Z1 is the height of this entry from this datum line. Similarly, this Z2 is the height of entry, height of outlet from this datum line, right? This Z2 is the height of outlet from this datum line. See, this Z1 and Z2 just we have explained. Okay, this Q amount of heat is supplied to the air. That means this Q amount of heat supplied to the air, and this work is done by the system. So be careful in in sign. Since this Q amount of heat is supplied to the system, that's why this sign will be positive, and this work is done by the system. That means we will get some positive work. So whenever heat is supplied to the system, this work is done by the system. As we know, we have explained in first law of thermodynamics for closed system. So these all are the properties of the air at inlet and outlet, right? Well, so in this equation, basically what we are doing here, just we are simply equating the energy at inlet to the energy at outlet. That means total energy of air at inlet will be equal to total energy of air at outlet, right? So this is the energy balance. So whatever total energy of air will be at inlet, that will be equal to total energy of air at outlet, right? So from this equation, I'm trying to understand this one. So this is our equation, right? This one. This is the first case when units. This is case 1 when units are in kilojoules. So be careful. Just I will discuss later on where this unit, we have to take care of this unit. So first case, this all quantity have unit is kilojoule, right? In this condition, what this is, we know that this small letters always used for a specific. Okay, this is U1 is the specific internal energy. If we use capital U1, that means this is the total energy. This small v1, this is a specific volume. If we use capital V, that means this is the total volume, that is m dot v1. Similarly, this H1 is the specific enthalpy, that means this is unit to be kilojoule per kg. If I am to calculate total enthalpy, that means we will multiply this mass, that is m into H1. So this will be capital H1. So capital H1 is equal to m into H1. Similarly, capital U1 is equal to m into U1. So this small, whatever the small abbreviation, this is used to denote the specific term, like a specific internal energy, a specific volume, a specific enthalpy. Whenever we multiply this term by mass, that will be total energy, like m into U1, this is total energy of air at inlet, m into small v1, this is the total volume of the air at inlet, m into H1, this will be capital H1, this is total enthalpy of air at inlet, right? Similar fashion, just we have to equate the total energy of air at inlet, that should be equal to total energy of air at outlet, right? So in this equation, so what is the total energy at inlet? This is capital U1. Capital U1 is the total internal energy of air at inlet plus P1 V1. This is the displacement work. This is P1 V1 is the displacement work, which is the form of energy. This is the displacement work of this air, which is already in terms of energy, right? This is plus half m v1 square. This is the kinetic energy of air at inlet plus mgz1. Since this inlet it is at height z1 from this datum line, so this will be mgz1. That means this is the total potential energy of air at inlet. M, this is mass of air, g is the acceleration due to gravity, and this z1 is the height of inlet from this datum line, and plus q. That means this q, a small q, this is actually this is a specific heat, okay, right? So this small q, this is here just I am using the total heat, that's why this is in capital Q. So plus q, that means what is this q? Q is this is q amount of heat is transferred into the system. That's why we are taking this plus sign. So this is plus q. So this is the total energy of air at inlet of the system. Just I am repeating once again. This U1 is the total energy of air at inlet. P1 V1 is the displacement work in the form of energy at inlet. Half mvn square, this is kinetic energy of air at inlet. mgz1, this is the potential energy at inlet, and q is the this amount of heat which is transferred into the system. This is the total energy of air at inlet. Okay, this will be equal to u2 plus this u2 is the total energy of air at inlet plus p2 v2, this is the displacement work is in form of energy at outlet. This half mv2 square, this is the kinetic energy of air at outlet. mgz2, this is the potential energy of air at outlet plus w is the work, just we are getting some work output from the system, and this is the work is done by the system, that's why we are taking here positive sign, right? So this is the very basic equation of steady flow energy equation. So whatever energy, total energy of air at inlet, that should be equal to total energy of air at outlet. So there are total 5 terms: u1, u, that is internal energy, pv is the displacement work in the form of energy, next term is kinetic energy, next term is potential energy, and this is heat. Okay, so this is the very basic important equation, and this is very quite easier to understand. So if you understand this equation, then you won't have any problem further. Okay, so just I am proceeding further. Right, now we know that this H is U plus Pv. This is enthalpy. Total enthalpy is the summation of internal energy plus displacement work. We know this equation. This H is equal to U plus Pv. So this U1 plus P1 V1 can be written in this form. This is H1, capital H1. So this is capital H1 plus half mv1 square plus mgz1 plus q. This is equal to capital S2. This is equal to U2 plus P2 V2 plus half mv2 square plus mgz2 plus w. So this is the first equation. When this, be careful, this unit of all terms are in kilojoule. This is very important. That's why I am saying this one. So whenever this in any numerical, you have to see what is the unit of this quantities. If unit are given in kilojoule, simply we have to use this equation flat. So you don't have to think anything extra. Simply you have to use this equation in this fashion, and further after discussion, just you may there might be some term this might be cancel out further. So this is the equation 1. This in this equation, this unit are in kilojoule. So this is H1 plus half mvn square. H1 is the enthalpy of air at inlet. Half mvn square is the kinetic energy of air at inlet. mgz1 is the potential energy of air at inlet plus q. Q is the heat transfer to the system. This is equal to H2 plus half mv square plus mgz2 plus work. Okay. Now we just proceed further. So be careful. In this equation, the unit of all the terms are in kilojoule. Well, now in the next case, case 2, in this condition, this unit are in kilojoule per kg. So be careful. In this equation, these units are in kilojoule per kg. That means what you have to do, we have to multiply the mass in this. If in this equation, if you divide by mass in this equation A, that means the unit of all the term will be in kilojoule per kg. So simply we have to divide the whole terms by mass. So if the equation is divided by mass m, then this unit will be converted into kilojoule per kg. So divide this equation by mass m. We get, just if you're dividing by mass m, that means this capital H1 is converted as small h1. This kinetic energy will be written half v1 square. This potential energy will be written gz1, and this small q, this capital Q by m. This is equal to small h2 plus half v2 square plus gz2 plus w. So this equation, in this equation, this equation can be written in this form. This is h1 plus half v1 square plus gz1 plus q. This is equal to h2 plus half v2 square plus gz2 plus w. So this is very basic equation. In this equation, one important point is there. This unit of all terms are in kilojoule per kg. Right? So in this equation, we need to be careful whenever this the unit of quantity are given in kilojoule per kg, we have to use this equation. So this is the specific enthalpy, this is specific kinetic energy, this is specific potential energy, this is small q. Okay, this is equal to, once again, this is whatever total energy of total specific energy at inlet, this is equal to total specific energy at outlet, right? So in this equation, this only we have to take care that the unit of all terms are in kilojoule per kg. This is third form, when units are in kilowatt. That means units are in kilowatt means, right, just we will explain further. In equation B, we know that this unit of all terms in kilojoule per kg, right? It is clear? Okay. Now we have to convert this unit in kilowatt. That means what you have to do? We have to multiply. If you multiply this term, that is a specific, this term that is kilojoule per kg, suppose that unit is in kilojoule per kg. If you multiply this term by mass flow rate of the air, that is m dot, then we will convert into kilowatt, right? For example, this is m dot into h. Suppose that this is a specific enthalpy. If you this multiply this by term mass flow rate of air, so this is m dot. Okay, this is m dot into h. This, what is m dot? This is kg per second, and h is kilojoule per kg, specific enthalpy. This kg will be cancelled out, and this unit will be in kilowatt. So if the equation B is multiplied by mass flow rate, that means in this condition we will get this unit of all term will be in kilowatt. So simply we have to multiply by mass flow rate to the equation B, so that it could convert it into kilowatt. So in this equation, just multiply the equation B by mass flow rate. We get, just we have to multiply this equation by mass flow rate. This is m dot into h1 plus half un square plus gz1 plus m dot q. Okay, so I have to separate this unit, this quantity. Just we'll explain later on. This is equal to m dot into h1 plus half u square plus gz2 plus m dot into w. Okay, so this m dot h1 plus half u square plus gz1 plus capital Q dot. What is this capital Q? This is the total heat supplied to the system in kilowatt. This is capital Q dot. Okay, this m dot into q. M dot is kg per second and q is kilojoule per kg. So unit will be in kilowatt. This total heat is q dot. Okay, this is the kilojoule per second. Kilojoule per second. This is heat flow into the system into kilojoule per second. This is equal to m dot into s2 plus half u square plus gz2 plus this is once again this capital W dot. This capital W dot, this is equal to m dot into a small w, right? So this is the third equation. This is equal to m dot into h1 plus half u square plus gz1 plus capital Q dot is equal to m dot into s2 plus half u square plus gz2 plus w dot, capital W dot. This is the third equation. Only difference is that this unit of all this term is in kilowatt. So overall, what we have conclusion, the whole discussion in this case 1, in the first equation, these units of all terms are in kilojoule. That means this is capital H1, the total enthalpy plus total kinetic energy half m square plus total potential energy, this is mgz1 plus q. This is equal to, this is the total energy at inlet. This is equal to H2, this is total enthalpy of air at outlet plus half mv and v2 square total kinetic energy of air at outlet plus mgz2 total potential energy of air at outlet plus w. This q is supplied to the system, that's why this is taken as positive sign, and when heat is supplied we get some work output, that's why here this positive sign is taken care. Okay, so in next case these units are in kilojoule per kg. That means we have to divide this equation, the above equation, by mass flow rate, by mass. So if you divide the whole term by mass, we will get this, instead of capital H1, this is a small h1 plus half u square plus gz1 plus a small q. This is equal to a small h2 plus half u square plus gz2 plus a small w. Okay, so in this equation, the unit of all the terms will be in kilojoule per kg. If they multiply this equation by mass flow rate of this air, that means the unit of all terms will be in kilowatt. So just we have to multiply this mass flow rate, this m dot into h1 plus half u square plus gz1, this plus capital Q dot is equal to m dot into h2 plus half b2 square plus gz2 plus capital W dot. This is the third equation of steady flow energy equation when units are in kilowatt. That means we have derived the steady flow energy equation in three different forms. In first form, these units are in kilojoule. In next form, the units are in kilojoule per kg, and this last form, the units are in kilowatt. We have only three important equations. All three equations are same. Only difference is that units are different. So in numerical, we have to be careful. What is the quantity of, what is the unit of this particular quantity? If units are in kilojoule, that means we have to apply this. We have to pick the equation number 1. If units are in kilojoule per kg, this we have to pick the case 2, the equation B. This is second equation. When units are given in this kilowatt, in this condition we have just will pick the equation 3. This units are in kilowatt. Simply we have to pick one equation. So that's why I have derived this equation in three different forms, three different equations. All are same, provided only difference is that these units of each terms are different, so that it could be easier to you to solve the numerical in shortest possible time. There should not be any confusion. We have to pick one equation. This equation will depend upon the quantity of this unit of that particular quantity which is given in question, right? So this is all about the steady flow energy equation we have discussed in this slide. We will discuss further in next session. Thank you very much.